All right. Could you please give me a +1 in the chat if you can see my screen and if you can hear me okay? And indeed, good evening, good afternoon, everyone. Thank you very much. Okay. So depending on where you're joining us from, in fact, it would be great to get a sense of what kind of times we are looking at. So if you could drop your location in the chat, that would be awesome just to get us started. I was trying to figure out a way that I can put up these slides on a touchscreen device, but that part of the setup is still a bit finicky. Hopefully, I will have that sorted by tomorrow. But for today, we will just run with these slides being streamed from my laptop, which means that I won't be able to annotate them by hand live. But the first couple of miniatures are kind of light on the computations. So hopefully that will not be something that we miss. All right, it's lovely to meet all of you from all over. Thanks so much. Thanks so much for your participation. So without further ado, I think let's just get started with the very first miniature. So we are going to, for the most part, go through these in order. Give you a heads up if there's any deviation. We also check if, okay. So there is some annotation that I can do here, but it'll probably not be very effective with just the mouse. Okay, so the first miniature is about the Fibonacci numbers, which you've probably encountered before. They are a sequence of numbers that traditionally start with 0 and 1, and they have the property that any element in the sequence further down is the sum of the previous two elements. So that's the sequence. Just a quick historical note to say that although the Fibonacci sequence is clearly named after Fibonacci, they were probably known to humankind from way before in various ancient math traditions, and in particular including Indian math traditions. So Hemachandra and Pingala are both attributed as having discovered these patterns by way of their work in poetry and in music. So that's just a quick historical aside. The Wikipedia page on the sequence is fairly rich in more information in case the historical or other aspects interest you. Would recommend clicking on this link from the slides to find out more. But this miniature is about computing Fibonacci numbers quickly, as the title suggests. So our first goal, and this may seem a little out of the blue, but we'll see why this is going to be useful, is to design a 2x2 matrix M, which has the property that when it's applied to this vector, which has some two consecutive Fibonacci numbers, gives us as output the next two Fibonacci numbers, not quite the next two, but at least it extracts the next one from Fn plus 1. So if you see, for example, 1 and 2, I want the output when this matrix is applied to, well, I should say 2, 1, 2 on the top and 1 on the bottom. I want this matrix to produce 3, 2, right? So I wanted to produce the next two numbers with this Fn plus 1 element being in common. And we'll see why this is useful in a second, because it will turn out that repeated applications of this matrix take us quite far down the sequence fairly quickly. But before we get to that, can we maybe just quickly reverse engineer what this matrix should look like? Let me see if I can get my Zoom window back so that I can follow along in the chat as well. Okay. Can't seem to find my Zoom window, which is a bit strange. Okay, perhaps somebody can post for me in the chat, and I don't know, I will see if I get a notification. Okay, the slides are at least moving. So what should the first row be if that's the desired outcome? Oh, okay. I think I managed to find my Zoom window finally. Okay, so I think it's clear to everybody. The first row should be 1, 1, and I think some of you have already jumped ahead. Thanks for the test message too. I think that helped me pull up the window. So yeah, the first row should be 1, 1 because Fn plus 2 is Fn plus 1 plus Fn, and we're going to get that by plugging in both ones there. The second row should be, as some of you have already pointed out, should be a 1, 0, because we want to kill the Fn and we only want to pull up Fn plus 1. So, so to knock the Fn out of the way, we have the 0 in the bottom right corner of that matrix, and the 1 is going to nice and easy pull out the Fn plus 1 term. So, so we have this matrix which has this nice property that if applied to a vector which looks like Fn plus 1 Fn, it gives us Fn plus 2 Fn plus 1. So in particular, M when applied to 1, 0, which is the first two terms of the sequence, is going to give us F2, F1, which is the second and the third terms of the sequence. You have zero-based indexing, so that's going to sound a bit funny, but that's what it is. Now, if you go ahead and apply M to F1, F2, the same pattern repeats and you get F2, F3. But notice now that F1, F2 was actually M applied to 1, 0, right? So F3, F2 is really M squared applied to 1, 0. What do you think Fn plus 1 Fn will be in general if you were to just repeat this process a few more times?
Times 1, 0.
Sorry?
Yeah, it will be the matrix Mn
Right.
times the column vector 1, 0.
Oh, absolutely. Yes, right. And we have that in the chat as well. So that's going to be M raised to N applied to 1, 0. And that's going to take us to Fn plus 1 Fn. And I hope that that's kind of clear from the way these operations pan out. What does this have to do with fast computation? Well, it turns out that if you want to compute the matrix Mn, M raised to N, you can do that by repeated squaring. So it does look like there are N matrix multiplications or N minus 1 matrix multiplications involved here, but you really don't have to do all of them. You could short circuit this computation by simply repeated squaring. So let's look at the simple situation, the relatively simple situation where N is a power of 2. There, for instance, you could just go M squared. If you square M squared, you get M to the 4th. If you square M to the 4th, you get M to the 8th, and so on and so forth. So each one of these arrows here reflects one matrix multiplication operation, one time that a 2 by 2 matrix is being multiplied by itself. Of course, the numbers are growing quite rapidly, but it's still, if you think of a 2 by 2 matrix being multiplied with another 2 by 2 matrix as being sort of the fundamental unit of computation here, then that's happening only logarithmically many times relative to n, right? So that's the nice situation when n is a power of 2. You want to compute, roughly speaking, the nth Fibonacci number, that turns out to be a power of 2, then you're in this happy space where you only need log many matrix multiplications for things to work out nicely. Now, what if n is not a power of 2? Can we still leverage repeated squaring? Are there any suggestions?
And use an Euclidean division.
Okay. Okay, there's also a suggestion in the chat to take the binary representation of n and work with the 1 bits. That's close to what I have on the slide, so I'm just going to follow up on that. So if you have a general number n, which is not necessarily a power of 2 by itself, then you can always write it as a sum of powers of 2. And in fact, there's a unique representation of this form, which just comes from writing it out in binary. So you pull out the indices, so to speak, that are 1 and raise them to the corresponding power of 2. And just by definition, that's what n is going to be. And so that's going to be m raised to the sum of these powers of 2. And that's going to, of course, multiply out. So now you have a bunch of individual powers of 2 operations, which we already know how to do. So for instance, m raised to 2 to the k1 is going to require only k1 operations. M raised to 2 to the k2 will require only k operations, and so on and so forth. So each of those individual powers are efficient to figure out. But then as you go along, these outputs have to also be multiplied across the board. So the point is that you only have at most, so the number of terms, so L in particular is roughly log n, because you only need log n many bits to represent a number whose magnitude is n. So you have log n many multiplications that go across the board, but each of the ki's is also going to be no bigger than log n. So that's also, each of those individual matrix products will also take roughly, well, certainly at most log n multiplications to compute. So overall, we manage this with only log n many 2x2 matrix multiplication operations. And that's about it for the first miniature. We have to watch out for the fact that the numbers grow pretty fast, and we will see from the next miniature that the numbers do indeed grow pretty fast. And you have to be careful about, if you were actually doing an implementation, you would have to be a little careful about dealing with large numbers as n becomes larger. But at least in terms of the spirit of why this is, why this makes for an efficient method for computing Fibonacci numbers, I hope that the main message is clear, and the fact that the matrix M comes in handy for expressing the nth Fibonacci number. That's kind of the main message here. Could you drop a +1 in the chat if this made sense so far? And if you have any questions, please feel free to either unmute yourself or put a question or comment in the chat, whatever you have. All right, awesome. What's the intuition for sequences being treated as vectors? So Manu, did you mean this in the context of what's coming up or what we have already seen? So here, I think we think of, well, the vectors that we are dealing with are these sort of 2-length vectors, right? So is your question pertaining to the intuition for this setup, or because in the very next miniature, we are going to literally treat sequences as elements of a vector space. So I just wanted to clarify if your question was regarding that. Okay, so the question is, can any sequence be treated as vectors? And that's actually something that, a bit of a spoiler alert, but in the very next miniature, that's going to happen in a very literal way. So, so maybe that's something that you can watch out for, and then we can come back to this question.
Ma'am, I was asking about in this context only, like the intuition to start thinking of consecutive numbers in a sequence as a vector and so on, and what I didn't understand the intuition or how that thought came in, or how to connect these two seemingly disparate things.
Yeah, so I think that's sort of a great point. In fact, I don't have it explicitly on the slides, unfortunately, but the author here does encourage us to think about whether this idea can be applied to other sequences as well, which are especially sequences that are defined recursively, and even more especially so sequences where the ith term depends on the previous 2 terms, or well, some 2 terms, let's say. You could look at more complex recurrences as well, but I suspect that when you do that, then the setup will become more complicated. As to how somebody comes up with the idea of, I mean, basically coming up with this equation, because this is kind of what is driving the whole argument. That's something that, to be honest, I don't know if I have a good answer to that. And I should probably have a bit of a disclaimer at this point that a lot of the miniatures do have this flavor that they will feel a bit magical, in the sense that there seems to be a very clever idea that sort of comes out of the blue, and they will typically leave you wondering how would anybody think of that. But once somebody tells you that this is what it looks like, you can sort of typically apply it to sort of at least superficially similar situations, and maybe with some cleverness to varied situations as well. So my approach to the miniatures has somewhat been that, okay, this is surprising and I have no idea how somebody would think of something like this. But now that we know that this pattern of thought exists, then we basically add that to our personal toolkit of things that we know and that we can hopefully apply in other situations as well, or just, enjoy the idea with maybe no particular application in mind. So I'm going to have to leave it at that. But if I have anything more coherent to say, I will come back to it either in the forums or when we meet again. So yeah, I hope that works.
Yeah, sure, ma'am. Thank you. And also, I was just quickly wondering if, like, when you think of sequences, series, and all, a convergence, divergence, and many other theorems, can all these be incorporated eventually into something like this? I mean, I was just wondering, ma'am.
Oh, you mean properties of sequence, like traditional
Yeah,
properties?
yeah.
Like,
Can that be thought of as part of this eventually? Because I study maths once in a while, like little bit. So
sure. No, I mean, I think that's a great question in terms of whether, so I think there are all these traditional tests of convergence that basically essentially a bag of rules, fairly well motivated rules, but nonetheless, I don't know if standard tests of convergence or lack of it can be thought of in linear algebraic terms, but I think that's sort of a great question. I don't know if somebody in the audience has any comments or pointers to that. I can't think of any off the top of my head, but it's a good thing to keep in mind. And I'll let you know if I come across anything.
Yeah, one of the things you could do is do some sort of ratio test and check whether this series is convergent, and Fibonacci is clearly not.
That's right. But I think also the question was about whether these convergence tests can be thought of, or if there is a linear algebraic way of, maybe if there's some trickery which is of a particularly linear algebraic flavor, which leads you to discovering properties of sequences. Like, I think
yeah, yes, ma'am. Like, for example, epsilon delta definitions or any other convergence tests. Let's say we are trying to find some way in a linear algebraic way that this is leading to something. So I was just thinking, I don't know the answer now.
right. So no, I think it's a very fair question. So for example, people who work with graphs often associate a matrix with a graph, and then there are a lot of observations which are along the lines of properties of the spectrum of this matrix tell you things about the structure of the graph and the other way around. So I guess this question would be if sort of analytical properties of sequences can be thought of as being related to something to do with, some sort of an object that comes out of the sequence that maybe lives in a vector space or something like that. So that's kind of, I think, the broad framing of the question. And I don't have an answer off the top of my head, but who knows? I mean, as we go through the miniatures, I think you should watch out for maybe such examples coming up.
One example that comes to mind on linear algebra is probably mixing time of mixing time of Markov chains, where Markov chains involve repeated multiplication of matrices. So I don't know whether that directly applies.
Yeah, I think that's a good point. So yeah, I guess when you start looking at random walks and convergence in that sort of a setting, then I think it's very useful to look at the transition matrix and consider its properties. So and I think there's some really nice material around that sort of thing. So right. So, okay. So I think, these are both prompts that are worth keeping in mind when coming back to. So thanks, Manu, for the questions there. I think there's a couple of other questions in the chat about, well, why is the number of digits in the nth Fibonacci number linear in N? I think that's something that will sort of come out of the closed form that's coming up in the second miniature. And once you stare at the closed form formulation for the nth Fibonacci number, it sort of follows from there. So I'm going to postpone answering this question to until we've seen a little more about the sequence. But also, if you kind of think about the growth of the Fibonacci numbers, so if you sort of draw out the recurrence tree, you will, if you just want some intuition, the idea is that the numbers are so large because the magnitude of these numbers sort of grows exponentially as you go along. So for example, if I give you the simpler sequence where the nth number of the sequence is simply the nth power of 2, right? So if that's 2 to the n, then you know that that's going to require n log of 2 to the n, which is n, that many bits to write down. So it basically turns out that the Fibonacci sequence has that sort of a magnitude explosion. It's not quite 2 to the n. It's some c to the n where c is greater than 1. It's also less than 2. But the idea is that you experience an exponential blow up as you go further down the line. And one way of just visualizing that is to draw out the recurrence tree for the Fibonacci series and sort of see how it pans out. But that wouldn't be like the most rigorous justification. So what we will see next time is like an actual expression that describes the nth Fibonacci number, and this intuition that I just described will hopefully be formalized by that. So hopefully that works. Ashish asks if we need additional time to compute the base 2 representation. I think for the number, before we can even write it out as a sum of powers of 2, and I think that's a great question too. And I think Jagdish already has a response. I was going to say that you can find the base 2 representation by repeated division, essentially by 2. So morally, that feels like log n operations, although I haven't, I'm not really thinking about getting into the complexity of each of those division operations. But yeah, I would still imagine that asymptotically it still comes down to log n. But I'm happy to be corrected if I said something terribly wrong with that claim. Okay, and also I think just to clarify, hopefully that this makes sense in terms of why is this overall log n? So if you look at the individual KIs, right? So that's, well, all these powers of 2 themselves are bounded by log n and magnitude. So each of the KIs, so we have a representation which requires log n bits. You do your appropriate floor ceiling to make that make sense. And so the largest power of 2 that we are going to encounter here is going to be a power whose magnitude is roughly log n, right? So, and all the remaining powers, if anything, are smaller. And also because there are only as many terms here, L in particular is at most log n, because each of these KIs really comes from an index in the bit representation. So there are only log n many indices to deal with. So, so the number of times that you're multiplying these products, that's a chain of at most log n multiplications. And each of those individual multiplications will not take us more than log n many steps to figure out, and that's by repeated squaring. So I think I had a question that was directed just at me in the chat about sort of clarifying this part of the calculation. I hope that that's clear, but let me know if it's confusing in any manner. So, yeah. Well, I mean, yeah, so I agree with Joel that specifically the claim being made is about, well, m raised to n. I think if you think of it as the sum in terms of powers of 2 is being given, then the number of 2 by 2 matrix multiplications that you have to execute is at most like 2 log n or so. That's basically what it is. But I think even coming up with the binary representation is not going to take you, yeah, I mean, that's not going to be a major overhead, I think. So we should be good in terms of the overall computation as well. So yeah. All right. But yeah, there's a good chance that I may not have said things that are completely accurate on that front, but I'm reasonably sure that this is an overall order log n algorithm. And technically speaking, I think it's a good exercise to figure this out eventually. What we are going to see next in the second miniature is sort of an algebraic expression that captures the nth Fibonacci number. So it's just a one-shot computation, which does not involve a sequence of multiplications. It involves a constant number of additions and multiplications. You just stare at it. It's like saying that something is 3 raised to n times 6 raised to n by 2 or something. It's a fixed expression, and you might be tempted to say that that's more or less a single. It's a one-shot computation for the nth Fibonacci number. Of course, it won't be fair to say that it's constant time, because you're looking at the nth Fibonacci number, you're looking at playing around with n-bit numbers. But nonetheless, I think it's an interesting question to figure out, to sort of figure out what the exact computational complexity is there, because it involves, I mean, the expression in question involves the golden ratio. So you will have to work with some appropriate computation, even though there are, in some sense, there are exact approximations that are useful. So I know exact approximation sounds like a bit of an oxymoron, but there's a way in which there's a manner in which we're going to make that precise. And if you look at the discussion prompts on the discourse forum, I actually have posted that as some sort of an exercise for us to think about. And there's also a pointer to actually a Twitter discussion that we had about what the complexity of the single shot computation might actually be. I don't think pinning it down is completely straightforward, but it seems like a fun and accessible exercise to sort of think about. So, okay, so I did promise that these are going to be half-an-hour sessions, and we are kind of on the half hour. So I'm going to kind of, whatever it means to say that we would officially stop, I'm going to officially sort of stop rambling at this point. I did imagine that we might get into a bit of the second miniature, but I think that deserves its own space. So I don't want to sort of rush it. But I think we've had enough of a teaser for what's coming up. What's coming up is a closed form expression for the nth Fibonacci number, which is going to be exciting. And there's also a fun challenge problem on trying to extend this technique to a different recurrence. So if you're an overachiever who has already looked up the miniature, then please think about the exercise, because I don't know how to solve it yet, and any help would be welcome. So once again, thanks very much for joining. If anyone wants to hang out or have a discussion, I'm happy to stay back for a little bit more, but let me just take a minute to stop the live stream so that we are good on the recording.